Um, Hello everyone. Today we will try to do some examples and design of beams. Let us consider one example. Design a beam of effective span 6 meter subjected to an UDL of 10 kilonewton per meter along with 100 kilonewton load. The beam is laterally supported. The thickness of the wall is taken as 230 mm. So this is given example. So we need to design a beam for the given loading. So your first step is to in design of beams, your first step is to you need to calculate the loads. You need to calculate the ultimate load. So let's calculate the ultimate load. So for this UDL of the beam given is 10 kilonewton per meters, and self weight, let us assume, so is not given, but you need to assume the what is the self weight of the you need to assume the what is the self weight of the beams. Let us take 1 kilonewton per meter is the self weight of the beams, and so it will be at 11 kilonewton per meters. Then ultimate load, so how to calculate ultimate load? Multiply with the 1.5, so we will get the what is the ultimate load. Similarly, calculate ultimate point load. So point load is also given, so calculate what is the ultimate point load. Means you multiply 100 kilonewton with the 1.5, so it will comes to be 150 kilonewton. Now I put it in a beam diagram, so you can see I represented the loadings. So it's a ultimate load. What I given here, it is a ultimate load. So now calculate reaction. So let's calculate the reaction. So reaction of this beam. So why VU means a shear force, CF force. VU means a shear force, ultimate shear force. How to calculate VU? So CFS will be maximum at the, we need to take maximum shear force. So in the beam, where will be the maximum shear force? Maximum shear force will be there at the supports, So if you find out the reaction, that will be the your maximum shear force. That's it. So let us calculate the what is the reaction. So how to calculate the reaction? You can check this. So it's a simply supported beam subjected to UDL and also a point load exactly at the center. Means it is a symmetrical loading. If you get exactly at the center, it is symmetrical. Then how to calculate? For UDL, total load divided by 2, and for point load, total load divided by 2. So our UDL is how much? 16.5 into 6 divided by 2 plus 150 divided by 2, it will give your total reactions exerted at the supports. So that will be your maximum shear force or ultimate shear force. Similarly, calculate what is the bending moment, maximum bending moment. So here mu, so you can check, this is symmetrical one. So simply supported beam subjected to UDL, what will be the maximum bending moment? It will be WL square by 8, WL square by 8. Same thing I did it here, guys. Please, you can check WL square by 8. This is for UDL plus WL by 4, 150 is W, L is 6 divided by 4. It will give the maximum ultimate maximum bending moment. So mu will get. This is how we need to calculate. If it's symmetrical, so this is how we need to calculate. Okay, guys. Then what is our next step? So next step is to guys, please. Next step is to, we need to find out what is the plastic. You need to find out what will be the plastic modulus. How to find out the plastic modulus? So let us find out what will be the plastic modulus. So plastic modulus. So you can see, guys, please, you can see this formula. So what is this formula? Is there in page number 53. Design bending strength. What is the formula for design bending strength? MD equals to beta B into ZP. ZP is plastic modulus. ZP into Fi by gamma m naught. So let's say to find out to select the section, to select the type of the sections, what I have to do, I need to find out what is ZP. Then how to find out ZP? ZP equals to MD into gamma m naught divided by beta B into Fy. So same thing we did it here. We can check. So it's is there in this formula, is there in page number 53. Page number 53. So what is that? Bending strength of the beam. Bending strength of the beam. So same formula we used here. We can check here. ZP equals to, guys, please, so to select the sections, I need to calculate what is the plastic modulus, means ZP. Plastic modulus is taken as ZP. So I need to find out that one. How to find out? By using that ultimate by using the bending strength formulas, I can you find out what is ZP. ZP equals to MD into this is maximum bending strength, MD into gamma m naught divided by beta b into Fi. So MD means you can now you can take ultimate load into gamma m naught is taken as 1.1 divided by beta b. So let us assume that my section is plastic. So initially I will assume it is a plastic. So beta b is taken as 1 into Fi is taken as 250. So it will be millimeter cube. Unit will be in millimeter cube. So that's how we need to calculate ZP. That's how I calculated ZP. Then whatever ZP you will get, guys, please, whatever the section model will get, I need to increase by 20 to 30%. So increase the whatever the values of ZP into 20 to 30%. So how to increase? So multiply with 1.20 into this values, it will give the 20% increment in the ZP values, means plastic modulus values. Okay guys, this is how we need to do it. Then from page number IS 800, from page number IS and from IS 800 page number 138 we need to, for required plastic modulus, for required, what is that, for required plastic modulus, we need to select the sections. Where I have to select? From page number 138 IS 800. There for required plastic modulus, we need to select the sections. So page number 1, what is the table number 46, you need to see, you need to select this one. Okay guys, so what is that? From IS 800 page 138 table number 46. From table number 46 I selected the, for required plastic modulus, I selected the sections. There they given what is the width of the flange, thickness of the web. This is called web, and 450 means is the height of the section set, and R1 is the root radius. This radius is taken as R1. So and TF is the thickness of the flange he given. So we need to take it from the IS code. ZP for selected sections, what will be the ZP means plastic modulus we need to take. ZE is also given, that is Z-axis. Then what is IXX? IXX is should be taken from, guys, please, steel table you take. For the selected ISWF 450, you take from the steel table. What is the IXX value? Steel table. So guys, please, you refer this steel table for IXX value. Value, so you refer steel table, for IXX values. Okay guys, this is how we need to take the data from IS 800 and steel table. IS 800 page number 138, from table number 46 I selected the sections, and I selected IXX moment of inertia values I taken from the steel table for the respective sections. Okay guys, this is how we need to do the steps. Then what is our next step? Now you need to check for the deflections. So now you need to check for the deflections, you need to check for the CFO, shear, maximum shear, and you need to check for the maximum bending strength, or moment of resistance. Let us check the deflections. We need to check for the maximum deflections. Then permissible deflections. What if the permissible deflections? You can take permissible deflection equals to span by 250. So what is the span? Length of the span is 6 meter, means it is 600 mm divided by 250. So it will be permissible deflection is allowed how much? 24 mm. Then you know the delta for now you know this delta equals to, for deflections for the UDL. So what is the deflection for the UDL? So 5 by 384 WL to 4 by EI plus WLQ by 48 EI. So this is for point load, and this is for UDL. I need to use. So guys, please maybe during the online classes I explained you where you have to take. So here you can check. So what is the deflections? If it is a UDL is there, what is the deflections? Delta equals to 5 by 384 WL to 4 by EI. So for if it is a point load, exactly the center L by 2, what is the delta? Delta equals to WLQ by 48 EI. My selected beam is combination of both. Then so I need to add both deflections. Okay guys, that's it. You need to add both deflections. Please remember here W, what you have to take? W you need to take here, please, this is star marks. So W you need to take, what is the W? W should be the working load. Please remember the load for the deflections check should be in working. So please remember, you need to consider working load, not ultimate load. Please remember guys, please, again and again I'm telling you, you need to select the working load. So here then delta equals to, use this formula, 5 by 384 ws to 4 by ei. This is for udl and this is for point load, wlq by 48 ei. Substitute all the values what you taken and taken. So here please remember, I can select it, you can check here, I taken working load, not a, I have taken working load, not ultimate load. Here also you can check 100. So 100 kilonewton. So I taken 100 kilonewton, that is working load. That is not a ultimate load. So this I calculated. So it comes to be 9.06 mm. So it is lesser than 24 mm. Hence it is safe. So this is how we need to check for the deflections. Please, one is permissible deflections, span by 250, and then what is the actual deflection? This is actual deflections. This is for actual deflection. This is actual deflection. This is actual deflections. So this is actual deflections you calculated, and it comes to be 9.06 mm. So it is lesser than the 24 permissible deflection, lesser than permissible deflections. Next, go for the check for the moment of resistance. So let's check for the moment of resistance. So let's check for the moment of resistance. Then section. So now before that we need to do the section classifications. Section classifications is number, table number 2, page number 18. Please go table number 2, page number 18. They given the different sections, like it is plastic, compact sections. They given different sections, the plastic, compact sections, semi-compact and slender sections. So we need to what you selected the section, we need to check that it belongs to in which sections. Is that belongs to plastic sections, is that belong to compact sections, or it belongs to semi-compact sections or slender sections. Then we need to go for page number. I already explained you people. So we need to go for page number 17 and 18. So we need to calculate what is the B by TF and D by TF based on the values. These are maximum limit values. So 9.4 epsilon and 84 epsilon. This is for plastic, this is for compact, and this we need to calculate and we need to check. So the value is lesser than 9.4 and lesser than the 8.4 epsilon and 9.4 epsilon. Say that I can say that my section is plastic sections. Like this we need to do it. What is the epsilon here? So epsilon here 250 by Fi. Fi is 250. So you can check what you will get is that epsilon you will get 1. Epsilon I will get is 1. Whatever the get here, epsilon I will get 1. So please remember, so this classification, it is then page number 17 and 18 and table number 2. So please, table number 2, there you need to calculate. First I need to calculate what is the B by TF and D by TW. What is B here? Please remember, half of the flange. B should be taken as half of the flange. You need to take. Okay guys. So now same thing I did it here. B is what? Half of the flange. B is how much? 200. So 200 divided by 2. TF means thickness of the flange. Thickness of the flange is 15.4. So thickness of the flange we selected, it is 15.4. The thickness of the flange what we selected, it is 15.4. We can check here guys, please. What is the thickness of the flange? Thickness of the flange is 15.4. What is the B? BF is the width of the flange, it is 200. So I need to take half of that one, that will be the B. So then that will be the B. So same thing you did here, you can check. So B by TF, so how much it is got? 6.49. So it is lesser than 9.4. Then similarly you need to do it for D by TW. There is a D is the depth of the web. So so this will be the, yes please, this will be the your D. This will be your D. So this will be your D. So D will be, I can calculate. How I have calculate? I need to deduct these two. So it means I can calculate H minus 2TF. I can do it, right? So H minus 2TF, that will be equals to D. H minus 2TF. I need this distance, means I need to deduct these two. H 450 minus 2 into thickness of two flanges. So same thing you did here, you can check. D equals to H minus 2TFI divided by TW means thickness of the web. So I got 45.56. So it is lesser than 84, so I can say that my section is what? It is plastic. My section is plastic. So if it is plastic, then I can take beta b values that equals to 1. So beta b values would be that equals to 1. Then from page number 53, so design bending strength md equals to beta b into zp into fi by gamma m naught. Beta b, already I know that my section is plastics, then I can take beta b as 1 value, zp. So I already selected from the so for the suit my sections, my selected section ZP is how much? 1760.59 centimeter cubes. So so I selected this one into 2 is 250 divided by gamma m naught. So I came to know what is my MD. So what is my MD? MD is how much? 400.13 kilonewton meter. It is greater than ultimate movement. So hence it is safe. This is how we need to check for the moment of resistance. Guys, please first you need to check. I need to check the which selection it belongs to. It belongs to plastic or compact or semiconductor slender. So for that I need to go for table number 2 and page number 18, and this thing I need to do. What is that? B by ratio. You need to take this one, the ratio of B width by flange width of the flange, half of the width of the flange divided by the thickness of the flange. That's you need to do. Then effective depth of the depth of the web divided by the thickness of the web. I need to do it. So based on the value you will get, what you will get, 6.49 and 40.56. You need to tell that which section it belongs to. So as for this, my value 6.49 and 45.56, it belongs to section plastic sections. So whatever my selected section is belongs to plastic sections. So please, you can see here what is that for plastic sections. B by TF is 9.4 is the maximum values. For D by TU2 please 84. Epsilon is 1. Epsilon is taken as 1. Why? Because 250 by 250, 1 by 2 is 1. Here you can check. Epsilon is 1. 250 by 250, 1 by 2 is usually epsilon is 1. So my value will falls this category. So it is, my section is plastic. Okay guys, this is how we need to do it, guys, please. This is how we need to do it. Then next step is to, we need to check for the shear. We need to check for the shears. So so let us take this one, design shear strength VD. How to check for the is the page number 59. Please go to the page number 59. They given design shear strength VD equals to AV into FI by square root of 3 gamma m naught. Here AV is the shear area for what is the rolled sections. For the rolled sections, AV is taken as H into TW. It is shear area, H into TW. H is the total depth, TW is the thickness of the web. So if you for welded, it will be D into TW, guys, please. So this is for rolled sections. So how we have to do? AV equals to H into TW. What is the H? 450 into 9.4. So substituting this, VD equals to design shear strength equals to 250 by square root of 3 into 1.1 into 4140. 4140 what? It's a 4140 for AV. AV what you calculated here. So it's AV. Then I got 543.234 kilo newtons. So it's greater than the VU. So it is greater than VU. Then I can say my whatever the selected section is safe against shear, against bending moment, and against the what shear, against bending moment, and against deflection. So like this we need to check for the selected sections. So this is how we need to do it, guys, please. So this is how we need to do it. Now let us consider another example. So here type of example is here you can see that they already given the what is the sections, what is the type of the sections. So then what is your steps? You need to find out, you need to check for the safety of the beams. So that's the given in this example. Let us consider this. Simply supported beam ISMB 350 at 52.4 kg per meter is used to over a span of 5 meters. The beam carries an UDL live load 20 kN per meter and dead load is 15 kN meters. The beam is laterally supported throughout. Check for the safety of the beams. We need to then safety of the means. You need to check for deflections. You need to check for deflections. You need to check for the shear force, and you need to check for the maximum bending strength. That is MD. Okay. So let us say, so ISMB 350 and 52.4. Then go to the what is that? Go to the page number Then go to the page number what 138 of table number 46 IS 800. Write down its properties, what is the height and all those things. This is 52.4 kg per meter, means if you convert it will be 0.524 kilometer per meter. It will be 0.54 kilometer per meter. So now I written the properties of those things. So it is taken from the IS code and steel table. The properties what I written is taken from the IS code and steel table for the respective sections. For the respective sections, I taken from the IS code and steel tables. Now let us calculate the first step. First, as we discussed it in the previous problem, your first step is you need to calculate the loads. You need to calculate the load, means you need to calculate ultimate load. Let us calculate ultimate load, self weight of the beam. So self weight of the beam, so already given it is how much, 52.4 kg per meter. If you convert kilogram per meter, it will be 0.524 kilogram per meter. So the same thing you written here. So self weight of the beams. Then what is the dead load of the beam is given 15 kilogram per meters. Live load of the beam is given 20 kilogram meters. Then what is the ultimate load? So ultimate load will be 35.52 into 1.5. So whatever the total load it will come here, it should be multiplied with the 1.5. Then so same thing I written here, you can check the beam subjected to UDL of ultimate 286. Then what will be the ultimate maximum, what is the ultimate movement? Ultimate movement will be WL square by 8. So same thing I read it here, you can check. So it will be 166.5 kilometer meters. Then what is the ultimate shear force? Ultimate shear force will be the reactions. Ultimate shear force will be the reaction. Shear force will maximum will be there at the reaction. So ultimate shear force nothing but the reaction. Then what is the reaction? Reaction is a symmetrical one, so it will be total load divided by 2. What is the total load? 53.286 into 5 divided by 2. So same thing you did it here. So I will get what is the ultimate shear force. Then guys, please, then we need to, now we need to check for shear, check for bending movement, check for shear, check for bending movement, maximum bending moment, and check for the deflection. We need to do it. Now let us check for the CS. Then design shear strength. So same page number, how much it is? Page number 59 of IS 800. Please go to page number 59 of IS 800. So page number 59. So you need to go for page number, how much? Page number 59 of IS 800. So go to the page number 59 IS 800. They given design shear strength VD equals to Fy by square root 3 gamma m naught into AV. What is AV? AV is a shear area. So that will be AV into H into T for rolled sections. What I selected is I section, right? For rolled I sections, AV equals to H into TW. H is the total depth of the I section. What is the total depth of the I section? Is 350 into T 8.1. 8.1 is the TW, thickness of the web. So I got 2835 millimeter squares. Then substituting these formulas, I got calculated VD. I got 371.997 kilonewton. So it should be greater than the VU. Yes, please, it should be greater than the ultimate shear force. So ultimate shear force is 133.2 kilonewton. So hence it is safe. Now let us check for the, now let's go for check for the bending. So you might be know in page number 53. In page number 53 I have formulas. MD equals to beta B into ZP into Fy by gamma m naught. So please remember, this is for VU lesser than 0.6 VD. VD is design shear strength. So my VD is falls below this, so in this category. So I selected this formulas. MD equals to what? Beta B into ZP into Fy by gamma m naught is a page number 53. Before that, we how to take this beta B ZP I know from the steel table or from the IS 800 page number 138, table number 46. You can select the for respective sections. You can select the what is ZP. Fy is 250, gamma m naught is 1.1. So what is beta B? Beta B we need to select based on table number 2 and page number 18. So we need to do this one. What is that? B by TF. So B by TF. So half of the flange width divided by the thickness of the flange. So 140 divided by 2. So I calculated is 4.92. It is lesser than 9.4. Similarly, D by TW you do it. What is the D? D is H minus 2F. Maybe I explain in this one. This will be your, yes please, this will be your D. This will be your depth of the web. So what is will be D? This will be H minus h minus 2tf, h minus 2tf, that will be your d. So same thing I did it here, you can check h minus 2tf. So I calculated what is d by tw, so is 39.7, so it is lesser than 84, means it will be the section is plastic, the section is plastics. For this we need to go table number, page number 18 and table number 2. So then this is how we need to, for selected sections we need to check which section it belongs to, is that belongs to plastic or compact or semi-compact or slender sections. Then now, so I already explained you, so I selected this one. Then where you have to get this ZP for the suitable sections, for the selected sections we need to go table number 46, page 138. So for ISMB 350, ZP is given is 851.11 centimeter cubes. So this is how we need to select from the, then substituting that formulas, then substituting that MD, this formulas, MD equals to beta B into ZP into Fi by gamma m naught. So I calculated MD equals to 193.43 into 10 raised to 6 Newton mm. So if you convert it into kilonewton meter, it will be 193.43 kilonewton meters. So it is greater than the ultimate, hence it is safe. So please remember, MD how much you got? MD is MD I got 193.43. So what is the ultimate? 166.5 kilonewton meters. Hence it is safe. So what I calculated, it is safe. So it is safe. So maximum bending strength. Then next, calculate for the, check for the deflections. Next you can check for the deflections. What is the permissible deflection limit? Permissible deflection limit will be what? Span by 250. So span by 250, you can check here, span by 250. Then what is the actual deflection? So it is a beam subjected to UDL. So it is a beam subjected to the UDL. So it is a beam subjected to UDL. You can check, it's a beam subjected to UDL. Then what is the actual deflection? Applied deflection delta equals to 5 by 384 into W raised to 4 by EI. So EI, so EI is 2 into 10 raised to 5 Newton per millimeter square. IXS value, where you have to take from steel table. From steel table you take these values. Steel tables, consider the what is the IXX and IYY. Steel table you consider the what is the value of this one. Okay. Then W is what? It's a working load. Please, again and again I'm repeating this. So what W will put, it should be the working load. So working load is how much? 35.524. Then delta I calculated is 10.60 mm. So it is lesser than 20 mm. Hence it is safe. So hence it is lesser than 20 mm. So what is the allowable deflection is 20 mm. So what I got here is 10.6 mm. So hence it is lesser than 20 mm, hence it is safe. So this is how we need to do it, guys. Please, this is how we need to do it. Thank you, guys.